This is a video for MEI Core Pure Mathematics, Matrices 5, 3x3 determinants and inverses, 5.2, the determinant of a 3x3 matrix. We've already looked at the determinant of a 2x2 matrix, and we can write that as either det t or t between two vertical bars like this. And if we know that this determinant is formed from this thing, that's the way that we would work it out. Leading diagonal, take away the other two elements multiplied together. If I use a slightly different notation, and this is more like we used in a previous video for 3x3, so I've got columns A and B and rows 1 and 2. And then if I want to find the determinant of A, I'm finding this determinant here, and that is how it would work out. So if we think about this in terms of 3x3 matrices then, if I've got a 3x3 matrix with these elements, then I can form a cofactor matrix for that, which will have these elements where A1 is the cofactor of this element here, so it would be the determinant of B2, C2, B3, C3. The determinant can then be found using any row or any column of the matrix. And all you do is you take each element in that row or column, depending on which you've chosen, you multiply it by its cofactor, and then the results are added together. So if we were to use the first column, that's this lot here, I would have A1 times its cofactor, so that would be this times this, A2 times its cofactor, so that would be these two, and A3 times its cofactor, and then add them together. And this is called expanding by the first column. I've used the first column elements and their cofactors. I don't have to expand by the first column. I could look at an expansion by the first row, and if we keep the same notation, then if I was expanding by the first row, I've got here A1, A1, so that's those two, and then B1, B1, that's this one here, and then C1, C1, that's this one here. And it doesn't matter which row or which column, as long as you apply the rule to the whole row or column, you will get the same answer for the determinant. And in practice, we choose a row or column for these things that has the most number of zeros in it, because that makes the calculation a little bit easier. Let's have a look at this example then. And for this example, I'm just going to use the first row. And actually, with simple numbers, it's very often the first row that we use by convention. So I want the determinant is going to be equal to, take the first element and multiply by its cofactor. So that's going to be 2, 3, minus 1, 4. And then the second element is 1, and times its cofactor is going to be minus 3, 3, 8, 4. And I've got a minus sign up here from the matrix of signs. And then finally the third element in that row. So I'm going to get minus 2 times this determinant, minus 3, 2, 8, minus 1. And that's going to be a plus there. That's the sign from the matrix again. So if I work those out, this is going to be 5. So that's going to be 8 plus 3 is 11. And then I get minus, that's minus 12, take away 24, so that's minus 36. And then I get minus 2 times, this is 3, take away 16 is minus 13. Work that on through, I get 55 plus 36 plus 26, and that gives me a total of 117. And there is that worked out for you. This has been expanded by the first column just to show that when you do it, whatever row, whatever column you do it by, you'll get the same result. So if you're finding the determinant of a 3 by 3 matrix, whichever way you work it out, it always boils down to this same relationship here between the individual elements. And you can show that that happens. You can try that for yourself. You can show that that always comes out. And hence, it doesn't matter which row or column you expand by, you're going to get the same result for the determinant. There's the summary for that then. The determinant is the same no matter which row or column is used. And as I hinted at earlier, you can save work by choosing the row or column carefully. And if one of the elements in the row or column is 0, there would be no need to calculate the cofactor for that element, and that can save you some time. And hence, if possible, you should choose a row or column which contains one or more zeros. Here's a second example then. We've got this matrix N, and it's worth considering expansion by the second row rather than the first. And if we do so, you see I've saved a whole section of cofactor here. And as I work that through, I get down to minus 53 as my determinant. So hopefully you can see the similarity between the determinants for 2 by 2 and 3 by 3 matrices. And if we had 4 by 4 matrices, you'd need to find 4 cofactors, each of which involves finding the determinant of a 3 by 3 matrix. It's quite long-winded to do that by hand, and hence we usually look for more automated methods for that, calculator or computer. And our final example then show that x equals 2 is one root of this equation. The determinant of this 3 by 3 matrix is equal to 0. In order to show x equals 2, we could just plug that in. So we could put in 1, 1, 2, 2, 2, 3, 2, 2, 0. And you could put that into your calculator and get out that it does indeed equal 0. Now, in order to find the other roots, we are actually going to need to find the determinant in terms of x. And one technique is to, again, look at which row or column you would use. And I would be very tempted to use this row here because it's got a 0 in it. So if we expand by the third row, so my determinant is going to be x times the determinant for 1x, x3 minus 2 times the determinant for 1x, 2,3 plus 0 times the determinant for 1, 1, 2x. And of course this bit I don't have to calculate. So this is going to give me x times, that's 3 minus x squared, and this is minus 2 times 3 minus 2x. And multiplying that out, I get 3x minus x cubed minus 6 plus 4x. And so I've got x cubed minus 7x plus 6 is equal to 0. I know that x equals 2 is a root. So x minus 2 is a factor. So I can divide this by x minus 2 to get the quadratic that's left. So if we do that division, that's going to give me x squared, and I'll get x cubed minus 2x squared, and that'll give me 2x squared coming out here, minus 7x. So that will give me plus 2x, which is 2x squared minus 4x, which gives me minus 3x plus 6 when I take it away, and that just gives me minus 3. So my equation is actually x minus 2 times x squared plus 2x minus 3 is equal to 0, and this factorizes to x minus 1 times x plus 3, and so my 3 roots are x is equal to 2, which we were asked to show, 1 and minus 3. So there's a lot of work hidden in that question. It looks fairly simple, but it is made a lot easier by choosing the correct row or column to do the expansion. The next and final video in this sequence is 5.3, the inverse of a 3 by 3 matrix.